Let's take a look at the homework on page 187 on related rates. And to start the homework, we're just going to practice some implicit differentiation because, as you know from the lesson or the lesson video, related rates is simply an application of implicit differentiation. You're going to use the implicit differentiation to solve an application problem, a related rate problem. All right, in problem number 1, we are given y equal to the square root of x, and we are asked to find dy dt. So we are differentiating the given equation with respect to t, not respect to x. And they have given us the information that the change in x with respect to time, and that's literally what that means, the d is the delta for change in x with respect to time, is 3. So I'm going to bring the equation over here. I'm going to make my pen just a little bit bigger. So y equal to, I'm going to make that x to the 1/2 power, and I am taking the derivative with respect to time. So d dt of the right-hand side, and I'll move this over. Let me erase that. Give me a second here. And then on the right-hand side, I'm doing the same thing. I'm taking the derivative with respect to time. That's x to the 1/2 power. And so we remember we have that variable disagreement. We have the variable disagreement on both sides. So the derivative of y with respect to t is simply going to be dy dt. And on the right-hand side, the derivative of x to the 1/2 power, we're going to use the chain rule. So I get 1/2 x to the negative 1/2 power. Here comes the chain rule, dx dt, because that variable disagreement. All right, we know that x is 4 and dx dt is 3, so we have 1/2 of 4 to the negative 1/2 power, and dx dt is 3. Watch this carefully because some of you have trouble with your algebra. So we have 1/2. That negative power goes to the denominator and becomes 1/4 to the positive 1/2 power times 3, and that 1/2 power is a square root, so that's 1 over the square root of 4 times 3, so 3 in the numerator. The square root of 4 is 2, 2 times 2 is 4, and so we get dy dt, the change in y with respect to time, is equal to 3/4, and this is not an application problem. It's just an opportunity to practice the implicit differentiation. All right, let's go on to number 3. Same situation. We're not doing a word problem yet. We are simply doing the implicit differentiation. So let's clear those annotations and let's go to number 3. So we have x, y, I hope you spy a product, equal to 4. And we are, you don't really have to write this, but I'm just emphasizing it. We're taking the derivative of the product of x times y with respect to t and the derivative of 4 with respect to t. We have that variable disagreement, so every time we take the derivative of an x or a y, we're going to need the chain rule. So here we go, product. Oh, I'll do that over here on the side because that's kind of a habit I have with you guys. So here's the first factor, the second factor. The derivative of x with respect to time is dx dt, and the derivative of y with respect to time is dy dt. So we have the first times the derivative of the second, plus the second times the derivative of the first. So that'll give us back over here, x dy dt plus product rule y dx dt, and then on the right hand side the derivative of 4 is still 0. The derivative of the constant is 0. We know that x is equal to 8 and dx dt is equal to 10. So I'm going to substitute 8. I don't know dy dt, that's what I'm looking for. This time I don't have a y value, so I'm going to have to do a little bit of work for that. And I know that, I'll put parentheses there, and I know that dx dt is given to be 10. And I'm trying to find dy dt, and that's equal to 0. So this is something that's going to happen a lot when you actually solve your related rate problems. You have one of the variables that you need, but you don't have another one, but you can substitute this 8 back into the original equation, so that's 8y equal to 4. And so if I divide both sides by 8, y is equal to 1/2. And so now I can substitute that in place of y. So that's your helper equation. You can substitute there to get values that you need. I'm trying to find dy dt. So I will get 8 dy dt equal to, well, not equal to, let me get the eraser, sorry. There we go. Plus half of 10 is 5, so I'm going to get dy dt by itself by subtracting 5 from both sides and dividing by 8. And so dy dt is equal to negative 5 over 8. So that's the implicit differentiation piece. We're taking the derivative with respect to t, and now we're actually going to break down some word problems. So let's clear the screen and let's go to number 15, which I've already done under the screen, so I'm just going to walk you through it and add some annotations in. The most important part of related rates or any kind of math application problem is reading and interpreting. So as we talk about in class, you have to go back to your math eyes. And so your math eyes have to see and they have to interpret. So let's walk through the problem. The radius r of a circle is increasing. That's important. If the radius is increasing, then the rate has to be positive. So the radius of a circle, r, is increasing at a rate of 3 meters per minute. So it's very important to create what I will call a box of knowledge. In other words, it is the things that I know from, so here's my, and I know that the correct pronunciation of knowledge is not knowledge, but it's helpful because it's the things that I know. So I will call it the box of knowledge. So this is the radius r, and this is the radius rate right here, radius rate. So radius rate would be denoted as the change in the radius with respect to time. Important for me to see right here with my math eyes that the radius is increasing, therefore I'm going to record that 3 as a positive value, and that's centimeters per minute. The reading is really, really important. All right, let's keep reading and see what we're supposed to do. Find the rate of change of area. So we want the rate of area. Well, how do we denote that? Rate of change of area with respect to time. So that's what I want to know. And then I know that r is equal to, we'll start out with r equal to 6 centimeters. All right, so now I'm going to take this box of knowledge and I'm going to think about, I got to have some kind of equation that relates the variables. So from the reading, I know that I am dealing with a radius. I know that I'm dealing with a circle, that's really important, and I know that I'm dealing with area. So those are my quantities that I'm dealing with. So hopefully the obvious equation that would connect radius and area is, yes, radius, circle, and area would be the area of a circle. So area is equal to pi r squared. So that is the equation that I want to take the derivative of. It has all my variables there. Now, one of the important things about related rates is do not ever substitute a changing quantity before differentiation, meaning right here, this radius of 6 centimeters, and that is centimeters, this radius of 6 centimeters, it's not a fixed radius. This circle is growing. So do not substitute changing quantities until after differentiation. Again, do not substitute changing quantities until after differentiation. If a quantity is constant, it is not changing, then you should substitute it before differentiation. I would take the time to write that down and maybe even just listen to that again and reprocess that. All right, so back to the problem. I'm going to take my equation that relates my rates, which is pi r squared. I'm going to take the derivative of both sides with respect to t. So the derivative, let's get a pen here. The derivative of a with respect to time would simply be dA dt. On the right-hand side, when I use the power rule, because remember pi is a coefficient, So the derivative would be 2 pi. There's the power rule. Whoops, let's go downward, not to the right. Yeah, the work goes downward, not to the right. So 2 pi r, and then the chain rule, there's my dr dt, there's that implicit differentiation. So after I have differentiated, now it is time for substitution, because I know what dr dt is, they gave me that. I know what the radius is, they gave me that. And so all I have to now do is substitute the numbers in, and I'm not going to use a calculator. I'm simply going to leave this as an exact value. Be careful with the units. You have to think about, again, it's really all about math eyes. We were trying to find what? The rate of change of area. We were trying to find the area rate. So think about it. What units is area measured in? Well, we know that area from geometry is measured in square units. Therefore, the rate of area would be square units per time. So centimeters squared per second. Minute, actually. This was in minutes. Yes. So if that said seconds, it should be minutes. And then all we're going to do for part B, I'm not going to really do it. We're just going to change the number from 6 to 24 and get a different number. It's a really good idea to write a sentence on an assessment. I will probably ask you to write a sentence to justify your reasoning and your conclusion. So I said when the radius is 6 centimeters, the area of the circle is increasing at a rate of 36 pi centimeters square. That should be per minute, because the rate of change of area is positive. All right, let's go on to number 18. That's this next one I asked you to do. So we start with the reading. And the reading, even though we're hearing, we're seeing. The volume, so this already tells us straight up we're going to be dealing with volume situation. The radius, here we go again, of a sphere is increasing, so that tells me that I'm going to have a positive rate at a rate. So the radius rate, which again we're going to denote as rate of change of radius with respect to time, is increasing, so I'm going to record a positive inches per minute. My goal, letter A, find the rate of change of volume. So right here, here's the key, volume rate. How do I record that with respect to time? dV dt is what I want to find when R is creating the box of knowledge is equal to 6 inches. And again, I'm not going to do both. I'm just going to do one value because it's just changing the number. All right, so now I have to find an equation that relates my variables. So I have R as radius, and I'm dealing with volume, and I'm dealing with a sphere. Now you might have to look this up. It's okay. The volume of a sphere is 4/3 pi r cubed. So this is the equation that I'm going to take the derivative of. Now remember, the spheres, think of a basketball or a balloon. If you're blowing air into a balloon, the balloon's getting larger, so the radius is changing. So this radius is changing. Therefore, it has to go in after the differentiation. All right, so let's take a look at the work here. So again, you see when I did this before, I created a box of knowledge. I recorded the things that I know. I wrote down my formula for volume. And so when I take the derivative of V with respect to time, which is right here, let me get my pen. The derivative is going to be dV dt. Then I'm going to use the power rule to take the derivative of the right-hand side. So there's the dV dt. 4/3 times 3 is 4. There's my power rule, pi r square. And here's the chain. Take the derivative of r with respect to time. You have to leave the chain behind, dr dt. Okay, now after I do the differentiation, I can substitute the values that they give me. Do the arithmetic, leave the pi as an exact answer. And since we're finding the rate of change of volume, remember volume is measured in cubic units, so I have inches cubed per minute. And then I go back and do the same thing with the 24, and it's just going to be a different number. All right, I'm not really too concerned about letter B. Explain why the rate of change of volume of the sphere is not constant even though the rate of change drdt is constant. Yeah, let's not worry about that right now. We can talk about that at another time. And then I wrote my sentence, so that's an important thing. When the radius is 24 inches, the volume of the sphere is increasing, and I did it for 24 instead of 6 for this one. Did I ask you to do 20? I did, so I don't have the work for that one, so I'll do 20. Tells us again that they will not always tell you what the problem is about, but this is your first assignment on this task. So all the edges of a cube, so that's important. We're dealing with a cube. And the edges, in case you're wondering, let's see if I can draw a cube on this little tablet here. Sort of. That's decent. So the edges are what you might call, well, they're not the sides, because the sides are it's where two sides come together. So those are the edges. All right, so the edges of a cube are expanding at a rate. Now, we could use, I'm going to use X for edges instead of E, because E is the natural, the base of the natural log. So I'm going to use X for the length of one of my edges, and it says the edges are expanding at a rate. So edge, here it is, right here, use your math eyes, edge rate, dx dt, edge rate, and they're expanding, so that's going to be positive 3 centimeters per second. How fast is the volume? So we want fast volume changing, so changing volume, fast volume, that's the rate of change of volume, so that's dv dt, find the rate of change of volume, when each edge, and I'm just going to do part B, when x is equal to 10 centimeters. So this is my box of knowledge, and so now I need an equation that's going to connect my variables. My variables include the edge, the x, and they include the volume. So I need the volume of a cube, and the volume of a cube is either a side cube or in this case x cubed. That's the volume of a cube. Take the derivative of the left-hand side with respect to time, which gives me dv dt. Take the derivative of the right-hand side with respect to time, which gives me 3x squared, chain rule, dx dt. So I've taken the derivative. Now I can substitute the numbers that I do know. So I know that the rate of change of the edge is 3 and x is equal to 10, so that's 3 times 10 squared times 3. 10 squared is 100. 100 times 3 is 300. Times 3 is 900. What were we finding the rate of change of? Volume. What is volume measured in? Cubic units. So this would be centimeters cubed per, what was our time? Second. So I would say when the edge is 10 centimeters, the volume is increasing at a rate of 900 centimeters cubed per second because dv dt is positive or greater than 0. All right, let's go on to, I think you have a couple more. One more. So 23. 23 is a really fun one. So we're dealing with volume again, and we have sand. At a sand and gravel plant, sand is falling off a conveyor and onto, it's a really important word, this is going to be the hardest one of this set. It won't be hard after you get used to it. A conical pile. So that's a cone at a rate of 10 cubic feet per minute. The diameter of the base of the cone, all right, so let's get a diagram going on here. So we've got sand falling and it's creating a cone. So here's, starts falling on the ground and then it starts building a cone. Maybe it looks something like that. So there's my cone. Falling off at a rate. So look at this right here. Reading. 10 cubic feet per minute. Cubic. What's measured in cubic units? Volume. So this time they tell me that dV/dt is 10 cubic feet per minute. Okay? The diameter of the base of the cone is approximately 3 times the altitude. So let's talk about that for just a second. The diameter is the distance, as you know, all the way across a circle. So there's your diameter. And the height of the circle is from the tip to perpendicular to the diameter. So there's the height. Maybe I'll do that in a different color, maybe in green. So there's the height. So that is the height of the cone. It's changing. And then the diameter of the base is approximately 3 altitudes. So diameter, D for diameter, is 3 altitudes. H for height, altitude is the height. Now, so we'll just stop for there right now. So we have H and we have diameter in terms of H. So this is keeping me with one variable. That's pretty important right there. All right, let's see what they want us to find. At what rate is the height of the pile changing? So I want the height rate, which is right there. So I want to know dH dt is equal to what when H is equal to 15 feet. Now remember, all these values are changing. Sand is continuing to fall onto the off the conveyor belt and onto the pile. Therefore, H is changing, so it cannot go in until after differentiation. So let's look at my variables to figure out an equation. I am dealing with volume. I am dealing with height. I'm dealing with diameter, which is connected to height. And I'm dealing with a cone. So the volume of a cone, and you might need to look it up, is 1/3 pi r square h. R like a pirate. Well, that's kind of interesting because over here in my little box, this is even the diagram is part of my box of knowledge. I have nothing about a radius. And of course, I know you're going, yeah, you kind of do. So let's come over here and take our, out of the box of knowledge, we know that the diameter is 3 h's. We know from geometry that a diameter is 2 radii put together. So in place of D, I'm going to substitute 2r equal to 3h. Therefore, that'll allow me to divide both sides by 2 and get r equal to 3/2 h. Now that's really important because over here I have 2 variables. Well, I have 3. I have a v, but see, I know something about a v, so that's a good thing. I have an h, and I know lots of stuff about, when I look at my box of knowledge, I'm looking back and forth. But I don't really know anything. I don't have a dr dt given. I'm trying to find dh dt, so that's part of the problem, obviously. I know for sure what dv dt is, that's given. So if I differentiate the equation as it is, I'm going to force a dr dt. I'm going to have a product rule right here, and that's going to force a dr dt into the problem. Well, I don't know dr dt, and that would be too many unknowns. So that is why over here, this is an important part of the box of knowledge, is connecting r to h. This allows me to substitute 3 over. So now that I know that r is equal to 3/2 h, I can come back over here to v and substitute 1/3 pi r is equal to 3/2h. That allows me to go to one variable, and I've got to square that, h. All right, now there's going to be lots of algebra cleanup, so I'm going to keep the 1/3 pi. I'm going to square the 3 halves and get 9/4 h squared multiplied by h on the outside. Then I'm going to keep the 1/3 pi. I'm going to multiply h squared times h cubed. I'm just doing this slowly so you can see all the simplification, because you want this as simple as possible before you start taking the derivative. I can divide 9 by 3 and make that 3/4 pi h cubed. And from there I can take the derivative. So that would become, and here's the work you can see right here. So I am up to this point right here. So 3/4 pi h cubed. And so then I'm going to take the derivative of v to get dv dt on the left-hand side. So that's what's happening right here. And on the right-hand side, I'm going to use the power rule. So 3 times 3/4 is 9/4. Decrease the power by 1, h squared, chain rule, dh dt. Then I'm carefully going to substitute my 10 for dv dt, 15 for the height. And then I'm going to square and do, now this is careful arithmetic, and probably I did not use a calculator. I just went really carefully. So what did I do? Right here, I started by multiplying by the reciprocal of 9/4 pi to get it to the other side times 10. So 10 times the reciprocal. Reciprocal of that is 4/9 pi, and that's where I got the 40/9 pi. And then I divided both sides by 225, which you can see right here. And then I reduced that by 5 and multiplied and got 8/405 pi. That will probably be for you the scariest part. So that is the related rate section. The calculus part of it is really not that hard. The big idea is reading it and interpreting it in place of r. So when I come back over here to the left-hand side, I can rewrite this equation. Notice no calculus yet. 1/3 pi. In place of r, I'm going to substitute 3/2h times h. No calculus yet. I'm going to clean that up and simplify. That's 1/3 pi times 3/2 h squared. H times h. All I did was multiply those together. No calculus yet. I'm going to clean it up again. I'm going to multiply 1/3 times 3/2. So that'll give me v equal to, the 3's divide out and give me pi/2h squared. So now I have a clean volume equation that I can easily differentiate. So let's uncover and see what I have here. Hopefully I agree with myself. Yep, so there's the cone, and there's the 1/3 pi, or yeah, me recording all of this stuff.